Okay, this video is going to be about intermolecular forces. We're going to look at 3 different types and go through how they form and a little bit more about them. So we're going to start with temporary dipole. Temporary dipole, it's what I tend to call them, but they've got lots of different names you'll see. Induced dipole, van der Waals force, you might see it. Dispersion forces, specifically London dispersion forces. Really, these are all the same thing. So, to start with, temporary dipole, if we had a molecule, I'm going to draw methane, CH4. I'm going to draw just a bubble representing where the electrons are in that molecule. So, generally, they're nice and spread out. The electrons all evenly distributed. But these electrons can move. So they move around, and probably most of the time they're going to move around in the same sort of directions, and they'll keep the charge evenly distributed. But every now and again it skewers, and what happens is the electrons all move to one side. Our bubble skews. And the electrons go to one side. This creates a slightly negative side. So I put 2 delta symbols here to show it's really very slightly negative. On this side, this becomes very slightly positive. So we've got a slightly negative side and a slightly positive side with the electrons around. The electrons will then can move again, and that's why this is only known as a temporary dipole. So dipole because it's got 2 poles, a negative and a positive. These electrons can move again, and the dipole disappears, which is why it's only temporary. But while it is there, it can very quickly form a bond, and that is known as the temporary dipole bond, or the induced dipole, or the van der Waals force, or the dispersion force. So if we have our temporary dipole here, and the positive there, if that's all that's there, it's not going to be attracted to anything. But if we have another CH4 molecule comes close, now the electrons in this are not going to like this negative charge because they're all negatively charged. So they're all going to move away. So they all push to one side, which creates another temporary dipole. Really, this is known as an induced dipole. It's been induced by this one. They're pretty much exactly the same thing, just slightly different how they've come about. But that's where the induced dipole name comes from. This dipole has been induced by this temporary dipole. But now we have a negative and a positive. Whenever we have those, we get an electrostatic attraction. So we get an attraction here between the negative and the positive. And that is our temporary dipole bond. So it's the attraction between delta delta minus on one molecule. So here's our delta delta minus side, so slightly negative side, and delta delta plus on another molecule. Can't spell molecule, not great for a chemistry teacher. So that bit, nice and simple. Next bit is we're just going to look at 2 different molecules that both have induced dipole bonds. We're going to compare CH4, which we've just seen, and C4H10, butane, and methane. Now methane has a boiling point minus 164 degrees Celsius. So in order to get methane to exist as a gas at room temperature, to get it to liquid, you've got to cool it down so much, or to minus 164 degrees Celsius, whereas butane is minus 0.5 degrees Celsius. So we can see that the bonds holding butane molecules together are a lot stronger than the bonds holding methane together. And this is because butane has a lot more electrons So it forms stronger temporary dipole bonds, or induced dipole bonds, or van der Waals forces, or London dispersion forces, whatever you want to call it. But because butane has more electrons, you could quickly work it out. It's probably about 34, 6 in carbon, 10 in hydrogen, so 34 electrons, only 10 in methane. So this temporary dipoles aren't as strong as these temporary dipole bonds. That is temporary dipoles. The next intermolecular force we're going to look at is permanent dipole-dipole bonds. So this occurs when we have permanent dipoles. We've just seen how an induced dipole occurs. We now have a look at non-induced dipole, permanent dipole. The classic example is to look at hydrogen and chlorine. So hydrogen, doing this off my top of my head, it's 2.1. I think chlorine is 3.0, but I might be slightly wrong on that. But it is higher than hydrogen. So what happens here is the electrons get pulled towards chlorine, making it slightly negative. Single dipole this time. Hydrogen then becomes delta plus. Now, unlike temporary, this is permanent. This will always be here. So we'll always have a slightly negative chlorine, we'll always have a slightly positive hydrogen. Now what happens if another HCl comes along is we'll have a delta plus and a delta minus. We've got dipoles, positives and negatives, so they're going to be attracted to each other. And that is our permanent dipole bond. Permanent dipoles are always there. Comes from the electronegativity values. Chlorine can grab the electrons, draw them towards it much better than hydrogen can. So these electrons are actually, from this covalent bond, a lot nearer chlorine, which is where we get that skewing then. The final one to look at is the hydrogen bond. And the hydrogen bond is just a different version of the permanent dipole-dipole. It's just a bit stronger. There's two things we're going to say about the permanent dipole. About the hydrogen bond, just to separate it out. It's a bond and it's between an electron deficient hydrogen. I can't spell deficient, D-E, I isn't there. So an electron deficient hydrogen, that just means a hydrogen with a delta plus. And this time it's between a lone pair of electrons. So a lone pair on a very well, that was impressive, very electronegative atom. So these are examples of these are oxygen, are nitrogen, and are fluorine. There are three most electronegative atoms. So what happens if we'll take ammonia, NH3, is our nitrogen has our three hydrogen bonds with a lone pair on. Now this nitrogen, very electronegative, so it's delta minus. The hydrogens are electron deficient, so delta plus. All the electron mass is being drawn towards the nitrogen, making these positive and the nitrogen slightly negative. When another nitrogen comes along, I'm just going to draw this slightly differently to help my diagram. As we have, same again, not positive, slightly negative nitrogen, slightly positive hydrogens. And so, we have a look, we've got a hydrogen bond, if we go back to the definition, it's from an electron deficient hydrogen. So we've got three of those, 1, 2, 3, 1, 2, 3. We see they're electron deficient because I've put delta plus by all of them. And a lone pair on a very electronegative atom. So here we've got nitrogen, very electronegative, and it's got a lone pair. and nitrogen here with a very lone pair. What I should say, it's on another molecule. So this couldn't hydrogen bond when it's already formed covalent bonds with hydrogens. But this nitrogen could covalent bond with either of these three, and this nitrogen with either of those three. It's easy for me to draw it like this. From this nitrogen and going to the lone pair. Lots of people lose a very easy mark because they'll go from a hydrogen, I'm going to put it in green because it's wrong, and they'll miss out the lone pair and go to the nitrogen. And that loses you a mark right there. So I'm going to rub that out. And that is 2 ammonia molecules, NH3, hydrogen bonding with each other. One interesting thing to add on this is how water behaves with other molecules. Now, lots of things can dissolve in water, and it's because it can hydrogen bond with them. So, if we have our O's and our H's, have that delta pluses, and then oxygen has 2 lone pairs on when it's bonded in water. If let's put methanol down. So this is methanol, which has an OH group, and I'll put the lone pairs on again. This has a delta minus oxygen and a delta plus hydrogen. And what can happen with methanol is because it meets the requirements for hydrogen bonding, we've got an electron deficient hydrogen, we've got an oxygen with lone pairs. This can hydrogen bond with each other. So from a lone pair on the oxygen to an electron deficient hydrogen, we can have a hydrogen bond. So these things can bond with each other, and we get them then dissolving. So methanol can dissolve very easily in water. Ethanol does exactly the same thing, and that's really the main alcohol we have in beers and wines and things like that, is this ethanol. Very similar molecule to this. So molecules with O and H's on can dissolve generally into water salt, depending on what else they're bonding with. But that is our hydrogen bond and our very quick look at all 3 types of intermolecular force.